We'll pick up where we left off. We just started. See, do you see my screen there?
Yep.
All right. We just kind of finished talking about the whole moisture availability and what do you do if you don't have moisture? Well, you irrigate. So we have a long history of irrigation pretty much anywhere where we didn't have enough water, natural rainfall. Irrigation was figured out. Even since really prehistoric times, we see irrigation that looks like this. This is like a kind of like a flood and furrow irrigation type system. And we see that in the Middle East, Mesopotamia, where we believe agriculture first got its start. So as you imagine, it's dry there, except where you're near water. In the case of Mesopotamia, that's in between where the Fertile Crescent is, where they say that agriculture was born, as in between the Tigris and Euphrates rivers. So they believe that agriculture kind of started just as supplemental moisture from periods of time where there was river flooding, but then they were able to figure out systems like this to use gravity to move water into furrows and then into fields. So today we still use that same irrigation. Whenever precipitation is inadequate, we see stuff like this, whether it's flood irrigation, flood and furrow irrigation, overhead, or drip. Here's some overhead irrigation, which very often used, comes in all kinds of different shapes and sizes. Often it is some sort of sprinkler system, whether that's on like a center pivot, like you see if you've flown over the Midwest, or really any dry area, you see the crop circles where they're on that center pivot irrigation system. The only downfall with with overhead irrigation is that you do lose a lot of water just due to evaporation. So it works pretty well, but evaporation is an issue. So in a lot of cases, we might use drip irrigation, and drip irrigation is by far the most efficient form of irrigation in terms of water usage. We usually see it more on horticultural crops. And in this image, it's like a soaker hose, which I don't know if you all have ever used those, but I wouldn't recommend them. They usually fall apart after, you might get more than one season out of them. But generally, a drip emitter type system, whether it's in a tape arrangement or drip tape, or actual hard pipe with micro tubing coming out of it and different types of emitters. Irrigation has really advanced over the years. It's gotten to the point where it's fairly simple to put in, at least the hard part of it, the hardware part. The controllers for it, which have gotten pretty precise, but are not quite user-friendly, let's say. They take a little bit more expertise to use these controllers. But nonetheless, it makes it very efficient in terms of water usage. I have heard some people say that when they switch to drip, they have issues in water table recharge, because you're just getting the plant just what it needs, and not enough of that water is actually going back into the water table. So in some cases, especially places where there's big elevation gradient, overhead might make more sense. In controlled environment agriculture, we almost always see some sort of drip irrigation. And that's mostly because overhead irrigation, the water sticks on the leaves much longer. or flowers, and that can cause rot, decay, and fungal issues. Generally, though, one of the big advantages of irrigating is that pests and diseases can be less troublesome if we're doing irrigated crops in dry climates. So we see a lot of agriculture being practiced in dry areas. The Central Valley of California is very dry. They have arid soils, but because they have snow melt coming from the Sierra Nevada mountains, they're able to really irrigate very well, at least when they have that snow melt. So that keeps down disease pressure from what we'd have in more moist areas. Another issue with irrigation is that we can introduce various salts to the soil, whether that is like a soluble salt coming from fertilizer use, or just salts naturally accumulating as they flow through just rock and soil. As that water flows through it, it can pick up, naturally occurring salts too. So in some places, a lot of research has been done in the ornamental world, at least, for trying to do xeriscapes, which are using kind of locally adapted plants to replace those that are that use a lot of water. So we'll talk about this more when we get into photosynthesis and kind of all the biological aspects going along with it. But just for now, just know that there are some different pathways of photosynthesis that allow desert plants and warm season grasses especially to use less water, but still maintain the same amount of photosynthesis. And the warm season grasses that do that are known as these C4 grasses. And some of our important crops are actually C4 grasses, like corn, sugarcane, also some turf grasses too. All right, so other than moisture, we talked about how climate is kind of looking at moisture and temperature. I think that really temperature is the most important factor in whether a crop can be grown or when we plant a crop in a given location. It's temperature really that governs our growing season. We look at it based on the frost-free period for the most part. So it's also important to note, here we are, I guess the first official day of fall. Yesterday was the equinox. So today, the days are beginning to get shorter and shorter. I guess they were getting shorter already, but quickly getting shorter after the equinox. We'll start to see how we have this energy balance, and there's kind of a lag there in between the seasons. So the summer solstice is not the hottest day of the year. It continues to get warmer, even though the days start to get shorter after June 22nd. And here we are on the, just after the autumnal equinox. It doesn't just jump into fall, and that's due to just the earth, the land mass, the soil, and also the ocean and water kind of absorbing some of that solar radiation and kind of radiating it back into the atmosphere. Causes it like a little bit of a lag effect. It's pretty neat. So we don't see that radiant heat loss varying as much by latitude as you might think. So we actually get a net energy gain at the equator and a bit of a net loss at the higher latitudes. So we also say that temperature is affected by altitude other than just latitude. As your elevation increases, your air pressure decreases and the temperature drops. And they say that that can be up to 10 degrees for every 1,000 feet in elevation gain, depending. Usually more around this 5.5 degree rise and for each 1,000, or sorry, drop for each 1,000 feet you go up. Also, generally, we have greater wind speeds at higher elevations, so that also contributes to that temperature drop. And what this means for us practicing, agriculture, if we're at a higher elevation, it changes what crops we can grow. If we think about that in a latitude sense, we could actually grow temperate crops, fruits and vegetables in tropical countries at higher latitudes. Of course, the opposite doesn't work. We can't grow tropical crops at lower altitudes in a temperate region because you can only go so low. But in tropical regions, they are able to grow some temperate crops at higher elevations. And we see that a lot in places like Mexico. There's a lot of agriculture being practiced up in the mountains. Tropical environment, but growing temperate crops at a higher elevation. We also have an issue with temperature where water vapor is able to absorb that heat radiation. So cloud cover can limit the radiative heat loss, which can be very important at night. Usually when we have, especially the first frost of the season, which won't be too long before it's here. Usually that first starts on a very clear, cloudless night because it's preventing that storing of that radiant heat, and it's allowing more radiative heat loss. So generally when we have areas with little cloud cover, we have big temperature swings. We think of deserts as being hot, but they tend to be very cold at night because they don't have water vapor and clouds storing that heat. So temperature is governed by the movement of heat, basically, the loss of heat. That radiant heat, first coming from that electromagnetic energy from the sun, absorbed by whatever thermal mass, then radiated back out. Of course, warm air rises and cool air sinks, and that is what we look at as the process of convection. And water and air are both equally important for that kind of convective heat loss. So we really need to look at that in terms of microclimate. If you're looking at an area to try to plant a particular crop, then you really want to look at where cool air is sinking and where warm air might be trapped. And those can be really good microclimates to grow particular crops. And we also need to think about how it's not necessarily bad to have cool air sinking somewhere. It just means that you might grow more cool season crops in areas where you have cool air sinks. Different plants for different places, and that's one of the big things I think is very important for us to try to get a grasp on, is we want to choose the right crop for the right place, and that's looking at both the macro and microclimate. So just looking at that in kind of on a scale here, in California, very important for a lot of vegetable, fruit, and nut crop production. In the Salinas Valley of California, it's a little bit higher up, so it's much more favorable for temperate vegetable production than the San Joaquin Valley. And they say that it's up to 10 degrees Celsius cooler in summer, so 20 or 30 degrees Fahrenheit cooler in the Salinas Valley versus the San Joaquin Valley. So in the San Joaquin Valley, they're growing things like almonds, whereas in the Salinas Valley, they're growing things like lettuce. Heat-loving versus cool-loving crops. And there's just a look at that. Partially due to that kind of convective heat loss, but also just due to elevation changes. So here's just another look at that. Warm air rising, cool air sinking. So we get frost pockets. That's not a place where you want to plant frost-sensitive crops. And it's Also interesting to look at the temporary temperature inversions and how those can have local effects on the microclimate in your spot, especially when you look at growing crops on slopes. And when we're kind of looking at this image, I'm thinking of this as maybe fruit trees here. The conventional wisdom and what I mentioned on Monday is that we might try to plant fruit trees on a south-facing slope because it's warmer. But if you think about it, it actually might be better to plant some frost intolerant from some fruit trees, like say apples or peaches or something. It might be better to plant those on the north-facing slope. It gets less sunlight, and therefore it causes the buds to break later because it's cooler for a longer period of time and probably more moist as well. So they might not be subject to the late season frosts that we tend to have so often, especially in our part of the state. In these mountains, we always have a late frost. This year we had one first week of June, we had a light frost. So if flowers are on trees at that point, it will kill the flowers. They won't produce fruit. We started to talk a little bit about how in the urban environment, it is making its own microclimate in terms of the heat island effect. Any kind of urban develop is affecting temperature, whether that's from asphalt or buildings radiating heat into the environment, or also from buildings kind of blocking wind as well. Lots of different things that environment. We also have issues with rainfall and runoff. All that impermeable pavement causes water to be channeled differently. So you don't get as much natural evaporative cooling in urban areas as you do in rural areas. So that's a big issue in urban environments. And issues if you're interested in practicing urban agriculture, and which is becoming more and more popular these days. All right, so we also have seasonal variations in the temperature in each zone, which has different implications on depending on what the plant we're looking at. If it's an annual plant or a perennial plant, what we're trying to do is, of course, maximize photosynthesis. Photosynthesis is going to occur it not necessarily in response to temperature, but the plant has to be alive. The cells have to be intact for it to be able to occur. So I think about how energy moves throughout the season in plants, especially thinking about perennial plants. Herbaceous perennials in temperate areas are going to die back to the ground. Depending on how hardy they are, that they will come back the following year or not. Woody perennials, of course, in some herbaceous plants will survive above ground and just go dormant and acquire some cold hardiness. We look at hardiness based on the USDA's hardiness zones. And they've defined these based on the kind of average minimum temperature that can be expected. So really the hardiness zone is not necessarily useful for us for annual crops. It's mostly useful for perennial crops because we're looking at kind of the lowest low in the winter. When we think about the hardiness zone, which you guys are kind of here in zone 7. We're over here in zone 6. They say that we're a 6B. So if we look at that on the map, we're going down in zone 6 as low as about -10 degrees. They have recently changed us to a 6B, which is -5 degrees. And for zone 7, you can expect your lowest low to go down to about 0 to 10 degrees. So question for you guys, is that accurate, do you think? How cold does it get in the winter for you all there in Keysville?
Not that cold. I mean, but I'm coming from the Midwest where I wake up and with the wind chill, it's like -30, -20.
Yeah, that's another issue to think about, how wind affects that too, and could affect the hardiness for plants as well. So for us, you know, when it changed to 6B and it was -5 degrees, usually we don't have winters that are that cold. However, a few years back, we had a winter where it got down to 16 below zero on our farm, which very abnormal, and that would put us another zone down. That would put us in zone 5 instead of 6. So either way, it's not necessarily something that is defined for the whole area. You're going to have different pockets of different microclimates. And we're in this area where we have a lot of elevational differences. So Mount Rogers, highest peak in Virginia, is just about 45-minute drive away. There in Grayson County, the temperatures get much lower than they do here in Washington County. So it's like a zone 5, and you don't necessarily see that on the map. I think they probably have a better map that is more advanced now, that you can get a closer look in particular areas. Like you can see here in Colorado, they got zone 5 kind of in the lower elevations, and of course in the Rockies, there's zone 4 with a few spots that are zone 3 in the higher elevations. So we run the gamut here in the U.S. We can go from really in Alaska, zone 1, and of course in Florida and even parts of California, we can get really to zone 11 and like in the Keys and some islands off of the coast of California. It's also interesting to note that this isn't, it's not just latitude here. You can see in California, for instance, we got zone 9 going all the way up into Oregon, where it's next to the coast. The coast tends to regulate the temperature a little bit more. And actually up even in Washington, in the San Juan Islands, you can get some zone 9, higher latitude, but so temperature is not just due to latitude. All right. This map is looking at, I think this is Ohio, but they're looking at the frost-free dates as governing the growing season. And so this map is just looking at when you can expect for the last frost to be versus the first frost, which, so last frost in the spring, first frost in the fall, that is the parameters of our growing season, quote unquote. There are plants that you can grow outside of that. Like our cold crops, your cabbage, broccoli, kale, all that stuff is a little more cold hardy. So we're not necessarily looking at the frost free period at that point because it's a frost tolerant plant. But for everything that most of our most important crops anyway, in general anyway, depends on where you're at. But most of them, our tomatoes, our peppers, our corn, we look at that frost free period as being the growing season. There's all kinds of different ways that we can try to manipulate the temperature around growing crops, whether that's by trying to manipulate the microclimate through thermal mass or by actually controlling the environment in a greenhouse. We also look at the vulnerability of fruit trees and their flowers, try to use radiational cooling or heating as ways to try to manipulate that temperature and prevent frost. And one way to do that is to mix air layers with basically huge fans, or spraying water over trees if we have the danger of a freeze coming up. The vineyard just down the road from me actually hired a helicopter service to basically fly over before the frost would settle and mix that warmer air rising with the cooler air that was sinking around the grapes. And it worked somewhat. So wind is also a big issue with that. And we have kind of regular winds, the trade winds, as well as just kind of wind being produced from the Coriolis effect, just from the rotation of the Earth on its axis. The trade winds, which are blowing towards the equator and usually carrying bodies of moisture from what are then drier places towards the equator. So that's a huge deal in terms of governing the climate in terms of moisture. We also have the divergence of prevailing winds kind of around 30 degrees latitude. Again, kind of with the trade winds mixed with the westerlies as well. So this is what really leads to differences in weather. Weather is wind basically carrying moisture to different places in high pressure, low pressure systems. That air movement and the composition of that air is what creates the dynamic across the US. So it's really important to look at that and try to almost become a bit of a meteorologist. And it shifts throughout the season. So in the US, we generally have, I guess, the opposite effect in the winter than we do the summer. The winds are kind of blowing opposite directions. So where does the wind blow in your area, across your farm, where you're trying to produce crops? Very important to look at as governing that microclimate. We also use vegetation. We use trees as windbreaks, shrubs. It's best to use evergreens for that. And they have a huge modulating effect on how air moves. They say that a tree can compress the air up to 100 times the height of the tree itself. All right, so real quickly, this last minute, I just wanted to point out kind of the composition of air in general. One thing here to note is that dry air is actually comprised mostly of nitrogen, 78% nitrogen. You would have thought that it was like oxygen and carbon dioxide, but it's much less. So we have a ton of nitrogen in the air, and that's very important for us to think about in terms of fertilizer use. So I think that was the last thing that I really had to point out for you guys. There's a few slides left here, but I think that covers all of the high points. So anybody have any questions, comments, or concerns?
If you want to keep going for a few minutes, since I used some of your first 20 minutes, you want to go a few, it's the same students in both classes. If you did want to say anything on them last slides.
You know, let me just go through these real quick. I think that's everything, though. Yeah, the whole idea here, the soil air is a little bit different than our, it's similar, but slightly different than atmospheric air. And one of the things we see with that is the soil bacteria living there. We talked about that in the ecology section, where bacteria are converting nitrogen in the air to ammonia that plants can use as a fertilizer. We're doing that same thing when we're producing nitrogen fertilizers through the Haber-Bosch process that was developed in the early 20th century. The difference is that the Haber-Bosch process uses a lot of energy, and soil bacteria are able to use very little energy. They're able to do that at, basically whatever ambient temperature it is. All right, so yeah, that's pretty much what I've got for you guys here. We think of the whole issue with climate change as just a carbon dioxide. There's a whole lot of other things there, but plants, of course, absorb carbon dioxide and photosynthesize and produce oxygen. So the most important point, I think, to recognize in the whole, climate change and trying to regulate that is that in agriculture, we have a better ability to sequester carbon dioxide than really in any other industry. So that could be possibly a way to get some extra money for farming in the future. Maybe. We'll see what happens. I think I mentioned the whole issue with the other greenhouse gases. That when sulfur dioxide, which causes acid rain, they dealt with that using a cap and trade system. It's not really an issue anymore. Methane is another greenhouse gas. They say it's like 20 times more noxious than carbon dioxide in terms of climate change, but it comes from animal production. If you're passing gas, you're releasing methane, right? Methane is natural gas. It's the same stuff that we burn to heat places. So nonetheless, not good when it's in the atmosphere. We want to try to keep it in the ground if possible. So anyway, we're seeing more interest developing in agricultural practices to sequester carbon dioxide and to help regulate the climate better. All right. Sorry for running through that so quickly, and sorry for coming in on you guys late this morning, but does anybody have any questions, comments, or concerns? No. All right. Well, I hope you all did well on your test on Monday.
As I graded did.
So that's a good thing, right? Everybody.
Yes. In fact, I'd almost would accuse somebody stealing my answer key because they did so well, but since I just made that answer key right before I gave them the test, I know it was legitimate.
Good.
Yes.